Okay, I run a business called Energywise Wales. I've been involved in renewable energy systems since, well, about 12 years. I've done many things, but a little bit of background about me, just so you know where I'm coming from. I used to be a teacher, then I trained as a carpenter, then I built my own house, and then I got involved in plumbing as a result of my own house and trying out the different renewable systems. I've got solar PV, solar thermal, and an air source heat pump. So I've got a few of these things at home. In that process, I set up a business called Energywise Wales. So what my plan was with the business was to look at the whole house, to look at and see, well, you've done the wider renewables. Let me click through this quickly. Yeah, to see, you know, it's not just one solution, as everybody's aware that we need to find a number of things to reduce our energy. So this is about energy reduction. So looking at a whole house solution, what can you do? What can you do at your home? So the first thing we can look at is heating and hot water solutions. So air source heat pumps are all being pushed at the moment because the plan is to reduce our fossil fuel consumption, because that is what actually increases the greenhouse gases and creates climate change. So we want to reduce our demand on fossil fuels, and that includes natural gas. So the government has got a huge push on for people to look at air source heat pumps. There's also ground source heat pumps. They get the heat from the ground. Air source get the heat from the air outside. Solar thermal is, we touched on that, that's for heating hot water, for your domestic hot water. So you turn the tap on, it comes out the tap. It's nothing to do with heating, although it can be. And then we look at the emitters. The emitters are things like your radiators. How are you going to get this heat out into the room? So you might have the boiler device, but how does that heat get into the room? So there's a boiler, there's the source of the fuel. It's not fossil fuel, so where's it coming from? And then how are you going to get that into your home? Things that can support that, as Marion has been talking about in detail, is your solar PV, because that's your electricity that obviously can drive these electrical devices. So solar PV is quite a good partner to run with heat pumps. We've touched on batteries. You know, you always are producing more PV generally at certain times of the year when you're producing it, maybe when you aren't able to use it. So you need some source of storage. And then of course there's EV charging, which we haven't touched on, which is your electric cars where everybody's been pushed to go. So again, it's the idea of having your own garage on the roof, your own fuel source, free fuel. And one other item then Marion had mentioned to me was mechanical ventilation and heat recovery. So let's look at this. So the heating system I look at is a bit like it's the heart. So the boiler is the heart, and the emitters are the blood vessels. It's how you get the heat through to the building. The mechanical ventilation, heat recovery, if you think of that as the lungs, because now we're hearing all the time is about trying to reduce heat loss. How do you stop heat going out? And people are talking about, I know you've had a chat about cavity wall insulation, external and internal wall insulation. You know, you're wrapping up the house to keep the heat in. But as well as keeping the heat in, you're stopping a flow of air. And that's a good thing, but it's also a bad thing, because how are you going to breathe? How is the house going to breathe? So mechanical ventilation and heat recovery is about the lungs. It's about creating a ventilating system that brings fresh air into the house and removes stale air. And in the process, it extracts the heat from the stale air that's going out. So it's not like opening a window, but we'll come to that later on. And then there's a thing here called, you mentioned geothermal, Marion, and the geothermal is kind of linked. I mean, we're not quite New Zealand. We don't have the hot geysers, but there is heat in the ground. You dig down a meter and you've got a constant temperature throughout the year. And that's where ground source heat pumps get their heat from. But if you combine this ground air heat exchanger, if you bring the air into the lungs through a ground loop, you can actually warm air up in the winter and cool air down in the summer. So it's a very clever thing, that, and I think we'll see more of that in the future. So, so we're looking at renovations. Where can you use these renewables? So most people have renovations. It's existing houses which they're trying to improve, or and these are retrofits, or they're new builds. So the idea is to reduce the amount of energy. As I always say to people, it doesn't matter what boiler you have, whether it's a gas, oil, fossil fuel, whatever, even if it's a heat pump, you want to reduce your consumption. That's how you're going to save money. That's how you're going to reduce your bills. And to reduce consumption, you've got to look at the build fabric. What improvements can you make to that building? Because the older houses are more like a sieve, they're losing heat. And we mentioned the ventilation. So it's about careful design. And I think this is quite an interesting little table here, that houses now, how much energy do you need to warm your house up? And at the moment, we've got here in this table, it says 45 watts a square meter to heat a house that was built in 2006. But actually today it's 35 watts a square meter. If we look back at a house that's older, only back to 1979, that's not that long ago, it's 188 watts a square meter. I mean, that's quite, it's quite shocking. And people didn't care back then about how much it took to heat houses, because gas was so cheap. And so we could heat our houses easily. Yes, Marion.
Just obviously that's before 1979. What about Victorian houses we live in?
Well, that's older than they're the same sort of thing. Yeah. They're just leaky sieves, aren't they? Yeah. So renewables in this particular property, just to so you can see, this particular property is a new build. It's one we did a few years back. Now I've got to minimize that. The house is 162 square meters. That's kind of average. The heat loss without the mechanical ventilation lungs system was 5.5 kilowatts. And with the heat recovery system, it's only 3.07 kilowatts. So that property in 1995 would have needed 10.3 kilowatts. And back in 1979, it would have needed 21 kilowatts. So you can see that, let me just see here. You can see that the way that the government's been going, the way that house building's been going, is to reduce our demands, and they have been succeeding. But the way that they do that is by insulating. But this middle picture here, this is a mechanical ventilation system, and that's really only suitable for a new build house, because it's a monster of a thing, and it's got tentacles that go all over the place, and because each room needs to have its own air vent. So right. So the heating system design, because this is what my main plug is how do we design a heating system? Because this is to give you an insight as to I'm just bringing up my clock so I can see how I'm doing for time on this. There we go. Yeah, the heating design, what do you need to take into consideration? What can you do at home to work with this? So even if you did nothing, even if you, even if you didn't change your current heating system, there are things you can do to improve, and you've probably talked about those. But when we're fitting a heat pump, it's really important that we find out where all this energy is going, and we reduce that, because heat pumps work on a low temperature. Your current boiler, gas boiler, would have a forward flow temperature into the radiators of about 80 degrees. Now that's really quite hot. And if you had your Christmas cards hanging over your radiator, I'm sure you've all seen them flapping around in the wind as the heat's risen off the radiator. With a heat pump, we're trying to reduce that temperature down to 45 degrees. So that's quite a lot. And so we look at where you're losing the heat. And one of the things, this is a thermal imaging camera, and I was reading recently in the paper, there's a community project, a bit like yours, where they've bought in some thermal imaging cameras, and they've gone out to people's houses and use these to help to identify where people are losing heat from their homes. So you can target the areas that actually really need the targeting. So that's quite a clever idea. So when we're designing a heat pump, you've got, and if any of you want to install a heat pump, this is what your installer should be doing. And if they're not doing this, then don't go with them. But they should be working out how much heat does every single room here need. And then they put that into a chart. They work out how much does each room need. And from that, they look at a design temperature. So there's current design temperatures we have to follow. Living rooms are 21 degrees, bedrooms are 18 degrees, and bathrooms, you will note, are 22. And that's because they're the room where you take your clothes off, and they've got to be the warmest rooms. So then from that, we calculate, doing our heat losses, we look at the windows and the types of the walls and how much insulation you've got, and have you got enough insulation in your loft, and have you got any insulation in your floors, and have you got draft proofing on your doors? All those sorts of things that are quite, everybody needs to look at. And we work out how much energy does each single room need. Okay. And when we've worked out how much each room needs, then we can decide how big your radiator needs to be. It needs to be carefully done. There's no more going into a house, licking your finger and saying, oh, that's a nice big wall, we'll put a nice big radiator on that wall. That's not the way it works anymore, because that nice big radiator might not be enough with these lower temperatures. So this particular house only needs 4.9 kilowatts of heat. So if we're looking at a radiator for these properties, what sort of radiators work? Because some people say only underfloor heating works with heat pumps. That's not true. Underfloor heating will give you the lowest flow temperatures, because it's a very low temperature. So if I said that radiators required 45 degrees, underfloor heating only needs about 35. So that's the most efficient, that's the sweet point. So if you can put underfloor heating in, that's great, but most people can't. So we look at the heat loss, we look at the flow temperature, and then we size the radiators. Now, let me see what my next slide is. Right, we size the radiators, and I'll come to that later because I've got a slide on that, but you can see where it's all coming from. It builds up to be a pattern. And so you can have underfloor heating, you can have a standard radiator, it works quite fine with a heat pump, or you can have something like this is a fan assisted radiator. So that's a radiator with little like computer fans along the top there that help to circulate the air. Do you know, like I was saying about the Christmas cards waving around on the top of the radiators? Well, they do that because the temperature's hot. But if you haven't got a hot temperature, you need a little fan to help push it out into the room. So those can be a solution. So how does a heat pump work? So here we've got what is an older style looking heat pump. You take 1 kilowatt of electricity, be it from your solar PV or from the grid. You put that 1 kilowatt into the heat pump, and a heat pump works like a refrigerator in reverse. So a fridge takes, if you put warm food into the fridge, if you put your hand at the back of the fridge, it's nice and warm at the back because it takes the heat out of the food and it chucks it out the back. So that's how it works. It uses its refrigerants and its compressor technology exactly the same as a heat pump. A heat pump is a fridge in reverse. And a lot of the early heat pumps were actually refrigerant units just put into reverse cycle. So this heat pump, you take a kilowatt of 1 kilowatt, 25p's worth of electricity, put it into your heat pump, and you can get up to 3.2 kilowatts out. In this particular one here at 45 degrees, you can get up to 3.7 kilowatts out. So that means you've got free energy. And that's why it's a renewable heat system, because you're getting something free from the air. The air is your fuel. And obviously, the warmer the air, the more fuel you've got, the cheaper your fuel almost. But these will work down to, most of the manufacturers say they'll work down to -20. But they're usually designed down to about Northampton I was checking is about -3, which is kind of average overall winter temperature. We'll come on to other issues around that. So that, if we just look here, that was a few years, that was the early Mitsubishi Ikedans, and that was whenever we started out in the business about 10 years ago. 45 degrees, it's called a SCOP, a seasonal coefficient of performance. That's what you want to be looking out for, because that's the efficiency of the heat pump. The higher that rating, do you see here at 35 degrees, it's actually 4.24. So that's why underfloor heating is regarded as a suitable, a very happy partner with a heat pump, because you get the highest output from your 1 kilowatt of electricity compared to 3.7 at 45. And that's why we don't really use them at 55, because that's dropped again. But now even there's a new range of heat pumps out, and they're using the new refrigerant gases. And these 45 degrees now are up at 4.13. And when I started out in the industry, they were talking about ground source heat pumps being more efficient because they got around about a SCOP of 4. So now the air source is easily getting 4. So this is just pretty much modern day heat pumps look like. Just to show you here that they work in the basis that this particular one is 8.5 kilowatts, 8.5 kilowatts at 20 degrees outside. It's constant 8.5 kilowatts until it gets down to -7. So that heat pump can provide 8.5 kilowatts down to -7. So some people are worried, you see, that, you know, like they say, well, what do we do in the winter when there's snow in the ground, there's ice in the ground? Will it work? Yes, it will work, but it will go to a certain level and then it will start to struggle a bit because there's less heat in the air. But your boilers would also struggle in the winter. You put on extra jumpers, or you put a little wood stove on, or, you know, you give it a bit of extra support. We have to design down to -3 for Northampton and -2 for us over here in Wales. We're a wee bit warmer than you, right? And then this is another type of heat pump. Again, you've got these temperatures, and something I want to show you here. See this graph here. It shows in the UK our sort of ambient our sort of heating pattern. So most people switch on their heating systems at 15 degrees. When the outdoor temperature drops to 15, we put the heating system on. But in actual fact, the bulk of the heating is required at maybe about 7 degrees from about 13 degrees down to about maybe 3 degrees, 4 degrees. That's the bulk of our heating throughout the winter. That's the biggest demand. So those minus temperatures I was talking about are really just for maybe a couple of weeks in the year. So that's another reason why heat pumps are now being seen as a viable solution, because those really cold days in the year are not very many. And certainly then, as you can see in this graph, that the efficiency of the heat pump starts to climb when the outdoor temperatures start to increase. There are different types of heat pumps. There's a low temperature, and they operate between 35, which is what I was saying for the underfloor heating, up to about 50. That's kind of pushing it. 50, you can get that. So, but then there's a high temperature heat pump, and they can operate up to 65 degrees forward flow temperature. MCS, as Marian's mentioned before, is the microgeneration certification scheme, and I've got a slide on that I'll tell you about later, because that's a very important thing in this. But the SCOP, do you remember I was mentioning the efficiency? They will only let you fit a system as long as it doesn't fall below 2.8 SCOP. So that efficiency, they're saying, if it can't deliver that, then don't fit it. That's your minimum standard. Now there's different heat pumps. There's a monoblock, there's a split system. A split system usually has a heat pump outdoor unit, and then it has a refrigerant compressor that is put indoors. Those aren't so common these days because most plumbers, they're not refrigerant engineers, and it makes it much more complex installation. What you'll find is it'll be something like this or like this, that everything that you need, this is the outdoor unit, this is the fan, this is the compressor, and indoors you'll have the cylinder. That's all you've got. If you don't get the design right, this is what happens. So it's really important that whoever you're employing to do your system gets those early calculations right. They get the right heat loss calculations. They work out the right amount of heat that's required for each room in the house, not just the whole house, but every room, that they work out the right size of radiator for that room. If they don't, your heat pump will get covered in frost like this. And how is it going to get heat out of the air if the air can't get to the evaporators? So this is what to avoid. So the heat pump, this heat pump, it could have been that it was too small, that it wasn't the right size, it wasn't big enough. The heat emitters were too small. If you had a ground source heat pump, it could be that the ground loop was too small. And that's the result, that the ice builds up on the outdoor unit. The heat pump is running all the time because it can't get enough heat out of the air or the ground. The customer's cold, or your house is cold because there's no heat getting to the radiators. And because the heat pump's running all the time, you've got high running costs. So that's really, really, really massively important to get that design right.
Dee, can I just pause you for a minute? We've had a question on the chat.
Kevin,
Right. Kevin, do you want to ask your question?
Well, I was just wondering how much the design stage of this costs, because I'm persuaded that this is very necessary. But if that prices people out again, it's of interest.
some installers will do it as part of the sort of agreement that they'll give you, what we used to do is we just say to people, we'll give you a rough idea of what size of heat pump, what cost it's going to be. If you're interested, then we'll do the design. The design could cost anything from about £300. I heard some people charging £500. Then some of the installers will say, we'll give you that money back if you go with us to install a system. Otherwise, here's all the calculations and you can go off and get somebody else to install it.
Thank you.
Okay. It'll be different for different people, different installers. So it's something to ask them. Yeah. Right. Ground source. Do you want me to talk about ground source? Right. So ground source heat pump is the same heating design is needed for the ground source that you use for the air source. Exactly the same. They've got low temperatures that they work with. They've got the same compressors. It's just instead of their fuel being air, their fuel is the heat from the ground loops. They do have better efficiencies than air source, but it's usually around about 1 kilowatt. 100%. So for example, if an air source heat pump is 4.1 SCOP, a ground source might be 5.1. You see, that's the efficiencies. They work on a constant temperature being in the ground. So it does make them good for colder locations. So that's why they're really popular in Scandinavia and Central Europe, because, you know, if you've got, you know, places where there's lots of ice in the ground throughout the year, yeah, I wouldn't necessarily think of putting in an air source heat pump, because air source heat pumps work harder when the air is colder. But Britain's a temperate climate because we're surrounded by sea. And so some people want ground source, that's fine. They are that little bit more efficient, but they are a lot more expensive to install. It also requires more space indoors, because that compressor, that unit has to be housed indoors somewhere, whether it's in your house or in your garage, or if you've got an outdoor shed or something you can put it in, that It can create a bit of noise indoors because you're bringing the compressor in. So, you know, like when your fridge or your freezer switches on and it goes, bzzz, you know, hum in the background, you can get that from a ground source. And if it's a cheap ground source, some of them can be quite noisy. So do check that out. If you're noise sensitive, people always say to me, oh, is the air source heat pump going to make a lot of noise? And I'm saying to them, well, don't worry about that, because really, when the air source heat pump's running, it's running in the winter time when your windows are shut. So you're not going to hear it. And in the summertime, it's on maybe for about half an hour maximum, just topping up your hot water. And if it's a day like today, you'll want to stand in front of it to cool down, because the byproduct's lots of nice cold icy air coming off from it. So do be aware that the ground source heat pump needs to have the compressor unit indoors. The newer units are much quieter, but it is certainly worth checking out if you're noise sensitive. The ground loop you need to have sufficient land. So if you're in a street of terraced houses, it's not the right product for you. If you're on a small holding or you're in a house with a very large garden, then that might be an idea. So you have these ground loops that are, they're a bit like underfloor heating, if you can think of that circulate, that's buried in the ground, 1 meter deep and 1 meter apart for each pipe. Or you can have this thing called a borehole, where they drill down into the ground. So if you don't have the space and you want a ground source heat pump, then you have to drill these vertical boreholes. And they can cost about £4,000 for each borehole. They're pricey. They put a lot of cost on. And Marion mentioned water as well as being a source for renewables. And yes, you can put a ground source heat, you can put a ground source heat pump loop in a pond. It has a pretty big pond, actually. It's not your standard, pond. It's a big area. And some people do put them in adjacent to rivers, but anything to do with water, you do need to check with your local water authority. For us, it's Welsh Water in Wales. You can't disrupt a water course without permission, so do check. Water source actually is the most efficient because there's heat in water. And if you were wanting to put a ground source heat pump in, the best land is boggy land. So you need to think, where is the land? What sort of field have you got? Is it, I live in a place called Sandy Lane, and it's not very good because it's got lots of sand and water doesn't hang about in sand, it disappears quite quickly. If you're somewhere where there's a lot of shale and rock, that may not be sufficient either. So you have to do a geological survey of the land to find out what's suitable and if that's the right way for you to go. And it is a lot more expensive due to all this groundworks. So we're finding that air source heat pumps are actually much better solutions these days. I think I've probably gotten along that. Efficiency, so versus ground source versus air source. The ground source is more efficient than air source, only by that one scop. The choice depends on your available land, the type of the soil, the geographical location, space in your house for the indoor unit, how much money you've got, because it's much more expensive. And then, as we're saying here, many more air source units are now achieving higher scops. And with the new refrigerant gases coming out, it's bringing air source into a much more competitive market. So this was just to show you the difference in the scops between an air source and a ground source. So 8 kilowatt ground source, 35 degrees flow, 4.83. An air source, 8.5 kilowatts, 35 degrees flow, 4, scop of 4. So we're around about that one that I was mentioning earlier. It's, it's, to be honest, I don't think it's a game changer. So this is the plant room. You know, how much we talk about plant rooms. So this is the ground source. How much space are you going to need for all this kit? Because Marion asked me to talk about what sort of things you needed to think about as householders and communities about fitting these. So the ground source heat pump requires more indoor space because basically you've got the compressor that sits inside. whereas with the air source, that compressor's on the unit outside. You may have a buffer vessel, and as I've said before, a buffer vessel is a reservoir of, let me just show you here, that's a buffer vessel. It's a reservoir of heating, central heating hot water, not for domestic hot water, not for your taps. This is for your heating system. And that buffer vessel then is the compressor switches on and it maintains the temperature in the buffer vessel. And that's, I think that one's probably about 200 to 300 litres, depending on the size of the house. So it's quite a big beast. There are some systems that are coming out now that mean you can combine. This has got a ground source heat pump here, and this is the domestic hot water cylinder. So that's a nice, neat solution where they're aware that many houses in the UK don't have an awful lot of space in them for all this sort of plant. If you're building a new house, so probably a ground source is more common than to consider for a retrofit. I haven't come across many where they've been retrofits, less perhaps out in the countryside on a farm. Thing to bear in mind is the noise factor. And as I said, the air source, the noise is confined to the external unit outdoors, so you're hardly ever going to hear it. I compare it to an oil boiler. I walk around my local community. We're off mains gas, and oil boilers, I tell you, they're just like rockets, you know, in the morning, you know. It's whereas the air source heat pump's got a little sort of a purr. It just hums in the background. Depending on which model you go with, of course, that's the other thing to consider. And a lot of pipe work. The air source heat pump, you prefer to have it close to the house, about 300 mil from the external wall. So that was the plant room idea. A lot of the heat pumps now have higher flow temperatures for domestic hot water that can heat it. This is the new refrigerant gases coming in. So they can heat those up to 75 degrees, which is, you know, quite phenomenal. So Legionella pasteurization was one of the things that used to be an issue with heat pumps, because people would say, well, you know, maximum temperature for hot water is 55 degrees. And Legionella bugs like to live in that sort of temperature, and we need to kill them off because Legionella is not a very nice thing to have. So we would normally have to fit an immersion heater, and the immersion heater tops it up from 55 degrees to 60. So it's only 5 degrees it's raising it on the immersion heater. It's not very much, but with these new refrigerant gases, you can use the heat pump to do that. So ripping and tearing away through this, I'm not breathing much. Are you all keeping up? Am I too fast, Marion? No, okay, good. Oh, right. Domestic hot water cylinders. So again, thinking about what's the impact on this on most people's homes. Well, you've got to think about a domestic hot water cylinder. As I said earlier, a lot of people got rid of their hot water tanks. They wanted this space. The old airing cupboard has now become a shower room or an extra bigger bathroom or what have you, you know, toy cupboard or whatever you've got. But out went the tanks and everybody clapped with glee. Now we want to bring them back, and everybody's thinking, oh dear, where are we going to put them? And it is a consideration. You do have to think, you do have to work out, where are you going to put these beasts? Now, some of them are just like domestic hot water cylinders, and some of them are like fridge freezers. You know, these are got lots of gubbins and expansion vessels at top of them. You've got to think about all of this because you need to find somewhere to put these. So it's not just like going into a terraced house and saying, right, we're going to fit a heat pump for you. There's lots to be taken into consideration. And this is one with a buffer vessel. Look at the pipe work here. I mean, it's a bit, you know, it's a bit amazing, really. You've got all the different controls and things. And a lot of those controls now are built inside these units. So that's the clever gubbins. So a hot water cylinder must be sized correctly. You cannot connect an ordinary, you might say, I've got a hot water tank from my oil boiler or from my gas boiler. Can't I use that? No, you can't. For the same reason that the radiators have to be bigger, the coil inside the cylinder that delivers the heat from the heat pump needs to be bigger. because you're delivering 55 degrees to the cylinder, not 80. So out goes your hot water tank, in comes the new one that facilitates a low temperature system. Legionella pasteurization I've mentioned. Location of the cylinder is important because you remember you've got to get the heat pump pipes from outside to wherever this is. So usually on an external wall is the best place for these, with the heat pump on the other side. That's the cheapest way to do it. A couple of pipes, bang, bang, in the back, into the heat pump, into the indoor unit, and away you go. So that's very much worth remembering. And it does bring me to the point of planning permission, because I don't know about over in England. I think you've got more lax planning permissions than we do. We can't fit these within 3 meters. They've got to be more than 3 meters from a boundary fence. But I think in England it's different. So again, check with your local planning authority. You can't just go in and bang it in where you want it. Just check what your regulations are. And of course, back to the lovely DNO. They want to know what size of heat pump you're fitting, because they want to make sure that their local grid can supply all the extra demand that's now being made of it. You've got EV chargers, you've got heat pumps going in, you've got a PV on the roofs. You know, the national grid is creaking. Right, where are we? Cylinders. You can combine these cylinders with solar thermal. So solar thermal is the panels that are on the roof that can provide hot water from the sun. They're the most efficient way of generating renewable energy. They can be up to 90% efficient in the summer months, whereas a solar PV panel is, if it's lucky, around 20% efficient. So that's why your solar PV panels are covering your whole roof. And when you see solar thermal panels, you've only got a couple of them there. So much, much more efficient system. But in terms of cost, similar cost for solar thermal and a new cylinder as it would be for a solar PV system. So solar thermal has dropped out of popularity because once it's done its job, it's heated your cylinder up. It says, yay, I've done it today. Switch off, 4 o'clock, 3 o'clock, 2 o'clock, cylinder's hot, and there's lots more sun out there. And it's gone, you've lost it. But if you've solar PV, you can use this thing called it's a brand name. It's an iBoost or an Imison. They're different brand names, but you can dump your surplus electricity from your solar PV into the immersion heater in your hot water cylinder. So,
Kevin's got his hand up, Darleen.
right, okay, sorry, oops, go away.
Kevin?
Thanks, Dee. Consistently fascinating material. Just a question, this is all a proper integrated system, which will take a bit of time, investment, planning and all the rest of it, and a fair bit of money.
Yeah.
I'm curious to know what your view would be on a pure, simple air conditioning unit, which you can get for about 500 quid, fitted would be a bit more, I'm sure, so that you've got one room being warmed without all the integration. Would that be pointless from what you know?
Well, the thing is that some people are looking at the idea of just heating one room, but then you've got to think about the build fabric and what impact that's going to have on the rest of the property if that's not getting proper heating. Is that what you were, have I got the right end of the stick there?
Yes, just the idea that you take the living room, whatever is your main place, stick a air conditioning unit as a air source heat pump, and then without all the integration and all the bigger investment, you could have a advantage.
I know that some people, I mean, I know one person who's fitted one of these. Mitsubishi make them, they can make them. They're just like a little fan coil unit that's fitted high up in the property, and it gets its heat from an external air source heat pump type thing. Yeah. They are cheaper, but it really isn't the way to go, I don't think. But if you're limited money, you can only do what you can do. But we'll come on to that, because I don't know if, certainly over in Wales, we've got Eco 4 starting, and Eco 4 is, they're offering free heat pumps, free heating system, or, you know, upgraded radiators and everything, and free PV to people on benefits, and to people whose combined income to the household is less than 31,000. So if you've got savings, that might be an issue. But there are schemes out there. There's another scheme that's got 5,000, it's called the Boiler Upgrade Scheme, and I'll mention that later, but there's £5,000 towards the installation of a heat pump.
Could I jump in just quickly? We were talking about Eco 4 last week.
Yeah.
We worked out that you had to be in receipt of a like a job seeker's allowance or
Yeah,
universal credit payment to qualify
that's right.
for it in England.
Yeah, all right.
The other thing is that you can install one of these heat pumps as long as it's like more than a metre away from the boundary.
Yeah,
It's something you were picking up earlier. That was
yeah. I thought England was a bit more sensible about that than Wales. Okay, don't tell them I said that. Right. Did that help, Kevin? Did I answer your question?
Yes, that did help.
Sort of. It's a little bit of a tricky one, but I think, you know, it might be a false economy, because but it's, you know, we've got to be realistic about this. If you've got the funds, put the heat pump in. If you haven't got the funds, then you've got to do what you can. And
it also strikes me that going forward, the design is going to improve, the cost going to come down. So, you know, to some extent, I accept what you sort of say. It might be a false economy for that reason.
A deep intake of breath when you say prices coming down. The only thing I've seen in the last couple of years is constant increases of 5% and 10%. I mean, it's all going up because raw materials are going up. I mean, you might get some, you might hope that there's more installers around and some people will do it for cheaper, but, you know, at the end of the day, the cost of copper is going up and wages are going up. So
definitely. Marion's got her hand up as well. She's been very patient. Sorry,
Marion.
It's all right. You said a minute ago about extra energy needed from the grid. I'm just thinking with ground source or heat, air source heat pumps, I wouldn't have thought it's taken a lot of energy from the grid. Am I getting it right? Am I understanding it correctly?
No, it doesn't. But it's each household is regarded that when a house is built, the district network operator allocates a certain fuse rating. So it's 80 amps generally. Some older properties were 60 amps. You might get one or two or 100 amps, but they look at that at a house and they say, well, okay, you'll have a fridge and a this and a that and another thing, and so if all those things are all operating at the same time, the demand from the grid is going to be X. And they might frown a bit if you've got if you're getting an EV charger, you should contact Western Power again about fitting that, because it affects the harmonics. So the heat pumps going into properties have to have studies done to identify if it's going to cause any disturbance on the grid, or disturbance to your neighbours. You know, their lights might flicker or something like that, or you might already be near the top end of your rating of appliances in the property if you've got a hot tub or a jacuzzi, or, you know, I mean, I've been in some properties where they've got, you know, two ovens, you know, 2 built-in ovens, and they do use them. So there's certain calculations that are done to work out the load requirement of the property, and the grid want to know. They want to make sure they can supply. Right. Okay, so moving swiftly on. Right. So this is to give you some idea, just the sort of space requirement that you might have. Okay, I mentioned buffer vessel, didn't I? Right, okay. So what is a buffer vessel? So as I said before, its primary role is a volume of hot water for the heating system. Not all heat pumps need it, okay? It really isn't needed. Sometimes, in a lot of cases, they're not used at all, but I'm mentioning them mainly because of this idea of surplus PV. People are wanting to think about ways of reducing their energy costs, and we're finding that if you can fit a bigger buffer vessel and maybe even put a couple of solar panels on it, you know, hot water panels, because remember that temperature guide thing I showed you at the very beginning that showed that the demand for heat was greater between was it like 12 degrees outside and about 3 degrees down, that in between those two was the biggest demand for heat. And there's heat in the air out there. There's maybe days when you could put a decent amount from a solar thermal, because remember, your solar thermal is much more efficient. So it just depends. Or if you've got a big PV system and you're not using the PV that you're generating, you could dump that in your buffer vessel. So it's just an idea. It's just something to throw out there for those people with the space and the spare cash to invest at this stage in the game. Okay, heat emitters. How am I doing? Oh my God, we've run over. Do I keep going or finish?
No, we've agreed till at least 9:15.
Okay, okay.
We're getting on.
Oh, I'm not halfway through yet. Okay.
I think just to say, Dee, if it does go over and people drop off, we are recording this, so if people miss
What,
it,
you want me to keep going?
if it's okay with you. I mean, obviously you don't want to be here till midnight, but it's entirely up to you. But we are recording it, so
well, I'll whiz on for a little bit longer. Okay, yeah. So heat emitters, right? Okay, as I mentioned before, you've got to do the heat loss design to work out how big the heat pump's going to be, but it also determines how big the radiators are going to be. So, for example, if we take, I've used the bathroom here in this one because bathrooms need the hottest, because it's 22 degrees the design temperature. But they've got the highest air changes because you've got fans to take out the moist air. So they're quite heavy demand. You see 74 watts a square meter. They're quite hungry rooms for heat. And what happens, I'm just highlighting this because a lot of people say, oh, I've got a towel rail in the bathroom, don't have a radiator. But a towel rail is for heating towels. It's not a radiator. So when you start to put a lower temperature into a towel rail, it just really just piddles it out. It's no use to heat your bathroom at all. So what we're looking at here is that when you're sizing a radiator for a low temperature system, you work out how much heat's needed. You look at it, you're running at 45 degrees, and that radiator then needs to be oversized by 3.1 times. That's a lot, 3.1. In the old days, they said it was 2 times. Now they're saying 3.1. So if the demand's 384 for the bathroom, you multiply that by 3.1, and you need something that's giving out 1.1 or 1.2 kilowatts, right? Right. Oh, and just to go back to that, so that means that some of the radiators in some of the rooms might be quite big. I mean, look at that one. If you multiply that by 3.1, that's going to be a beast of a thing. You know, it's going to be 6 kilowatts, a rough guess. So, you know, a 2 kilowatt radiator is it's probably about 1400 by 600 high, double panel. We'll come back to that. So just things to bear in mind. Right, okay. So this is why underfloor heating, people say, oh, underfloor heating works really well with it, because you've got this great big radiator on the floor. And things that need to be remembered there is how far apart the pipes are spaced, because just like the radiators need to be bigger, you need to make sure you've got enough pipe in the floor. So in the old days, underfloor heating was fitted with maybe 300 mil spacings between pipes. But now we're putting it in at 150 as standard, and in some cases 100. So works very well, but you need to do the calculations, and even what finish you put on the floor is really important, because if it's laminate or carpet or wood, it each has a different impact on the floor, because wood's a very good insulator, but then it stops all your heat getting out. So that's really important to remember. This is another type of underfloor system. It's an overlay. It only takes up 17 mil of height. So that's good for a retrofit if you're putting it into an existing house and you don't want to, you can't take much off your door height. So that is quite a successful system. I'm going to speed through these. That's a way of doing it between the joists. If you've got joists, so you can put them in on little supports, and then the pipes go in these tracks. Another method is to lay it on top of the floor. So this is one that comes with some insulation on the back. And again, the pipes are fed through these trackers. So it can go on existing properties. These are the sort of standard radiators that we're looking at. A K2. Again, if we go back to those outputs, 742 heat loss, 45-degree flow temperature, oversize factor of 3.1, you need 2.3 or 2,300 watts. So a standard radiator that would deliver that is actually 600 by 1400 K2. That's the deeper one, see? Not one of these wee skinny single radiators. So not even a P+, which is a double panel with one convector. You need a double panel and a double convector to be, it's really what's used with most heat pump installations. If you haven't got the space for those big beasts, then as I said before, you can look at the fan-assisted radiators, because they don't need the oversize factor because they've got the fans in them, see, to help to shift the heat around. So that would be your big radiator oversized, and that would be your fan-assisted radiator if you didn't have the space. There's the little fans in them. They're very sleek, but they're a bit more expensive, and they will require an electrical point as well as the plumbing points. I'm going to flick past that one. And we've got solar thermal. Marion, what do you reckon? Have you had enough?
I'm engrossed. I am. I don't know about everybody else, but I'm really engrossed, and also about you.
Okay, well, solar thermal. Okay, here we go. Right. Okay. So it's the most efficient, and it's what I cut my teeth on when I get into plumbing. I fitted a lot of these systems, mainly flat plates. I've done my fair share of skipping around on roofs, but it's the most efficient. It's 90% hot water throughout the summer months, 70% throughout the year. Because remember that what it does, it's preheating. You get a big cylinder. I don't know if you can, my image is on the screen, if you can see me, but you get a big hot water cylinder, and at the bottom of the cylinder, you get two coils in it, and the bottom coil is your solar hot water coil. So that's a preheat. That's always heating the water, and your boiler coil is the middle connection on the cylinder. So the middle connection doesn't heat the quantity at the bottom. That solar volume is dedicated solar volume just for the solar hot water. So let's say in the winter, your water is normally coming into the house at about 5 degrees, 7 degrees, because it's cold. If you've got 20 degrees or 30 degrees coming off your solar thermal, warming up that water in the bottom of your cylinder by 20 degrees or 30 degrees, then your boiler isn't working so hard to top that up to 50. And once the molecules start moving, which I think is beyond 10 degrees, if there's a scientist in the room, I apologize, but I understand that that once they start to move, then it's easier to get more heat out of them. So actually, by having some solar thermal on your system, or even the heat dump would do this, but from the PV, but they do really help through the winter months, is what I'm trying to say. Even though daylight hours are less, the nights are longer, there's less heat in the air, but they are still very effective. And especially in spring and autumn. And this is where people with underfloor heating and heat pumps sometimes are using these to contribute to the heat demand. Because once you've fitted these, it's only a wee pump, it's nothing to run them. It's peanuts. So, right, but the solar thermal market has shrunk because of many manufacturers have withdrawn their products, mainly because PV has become so popular. Because, like I say, once your solar thermals have done their job, they switch off and they're just sitting around there, nothing to do. I'm bored. But the PV can do its job, and then it sort of says, oh yeah, right, I've finished that now. What's next? Come on, bring it on. Give me an electric car. I'm ready. Give me a fridge. I'm waiting to go. But with solar thermal, it's just a one-trick pony. Unless you've got a buffer vessel, that is. Then the solar thermal can do lots more. So some costs: 2 flat plate collectors, a twin coil cylinder with the scaffold. You're looking around about £6,000. And didn't we say a solar PV system was somewhere around £5,000 to £6,000? So, that kind of, the big expense is a cylinder,
Yeah, I think the it was 6,500 for the solar.
Yeah.
PV.
Yeah.
Going back to the, sorry, Darleen, going back to the air source and the ground source heat pumps, did you say how much those systems might cost?
Not yet. It's coming.
Okay.
Coming. Do you want to keep rapiding on? Right. Okay. So you were talking renewables, renewable heating. I'm going to just throw in a wee bit about biomass boilers, because I don't know if there's anybody there with a nice big house that can't be heated with a heat pump. Because remember, heat pumps are low temperature, and some houses just can't cope. There's nothing you can do about it. That's life. So biomass, they burn the pellets. The thing to be remembered there, some of them need to be fed manually. So you've got these sacks, and they're fed into the hopper. And it's something really worth bearing in mind, because if you're that little bit older, you might can throw the sack around now quite happily, but in 5-10 years time, are you able to? And it's worth remembering. So some people are looking at automatic feed, that you're not having to throw these sacks into the pellet hoppers. Their biomass boilers are excellent for these high heat losses, hard to heat homes like country houses, old farmhouses, stone built. Some stone built are fine for heat pumps, don't get me wrong, but some of them are just maybe listed buildings, those sorts of properties. They are very efficient, and some of them you need to look at the particle emissions, because that's the thing that people are going on about now, that they can be affecting the air quality. But if you get the right unit, we used to install ones by Windhager, and we felt they were a pretty decent one. But if you're wanting to fit a biomass boiler, it's a direct replacement for your oil boiler, for example. And you don't need to change your radiators or your cylinders, so there's a lot of savings there. But you do need to think about where you're going to put the pellets. That's the big question. Cost, about 17 to 20,000, I should think, and you get 5,000 back on the boiler upgrade scheme. Pellet stores, so there's a manual hopper, can be delivered in bags or in individuals, and you have to be careful where you store these, because moisture content can affect the burning quality, so they can't get too wet. You can build a dedicated little store for them, or you can buy a silo. But again, it puts off the install costs. So that's the cheapest installation there. But like I say, you have to have the strength to lift the bags up and put them in. Industry standards. Yes. Shall I go on to these? I don't know what happened with the slide with the costs for the heat pumps, but I would say probably heat pumps, you're talking about air source, probably from 10 to 18,000, depending on the size of the heat pump. And that's with the heat pump and the cylinder. And then with a ground source heat pump, you're probably looking more like 20,000 up, because you've got all the groundworks in addition. And with boreholes, then you're probably looking at 30,000. What else is on that? That's it really for the minute. I'll come back to it. I was just going to touch, I know you mentioned it, Marion, but it is really important. There are industry standards governing the installation of heat pumps, and MCS is the industry body, a bit like Gas Safe. So anybody who's fitting your system must be MCS accredited. The product they fit must also be MCS accredited. So it's really important that those two are the case. And MCS stipulates the design parameters. So, you know, I was talking about the heat losses and the temperatures for the rooms, and all the rooms must have radiators the right size. That's MCS. They are saying, if you don't do that, we won't give you your certificate. If you don't have your certificate, you can't get these grants and fundings. And for PV, you can't connect to the grid. They rigorously vet members. I hate it. Every year we were inspected, and they come out and they go through all the paperwork and they spot check, and you know, I'm sweating by the end of it. I'm just so glad each year when we get through it. But there's an annual inspection. They check the quality management system, and then they go out to a site and they inspect that as well to make sure that your installation standards are meeting the industry standards. So their main thing is to try to keep the industry standards up, to ensure quality, both the products and the installations, improve performance so that you're not getting, they're trying to keep the cowboys out basically. I'm not sure they're necessarily succeeding, but that's the aim. And they're trying to reduce the risk to the customer. So that's what you're looking for, MCS certified. If you go onto the website, you can find a contractor, or you can find a product directory. This is what you'll get here. You can check out the installers to make sure if you're looking for an installer, you can go on there and see who's located near to you. Just put in your address and what technology you're after, and you'll be able to find them. And that's the boiler upgrade scheme I was mentioning. It's 5,000 towards the cost of an air source heat pump, 6,000 towards the cost of a ground source heat pump, and 5,000 towards a biomass boiler. To be eligible for it, you have to have an MCS certificate. So that's to make sure that the public funds are being spent wisely and that you've had your installation properly carried out. But you also need an energy performance certificate. And that energy performance certificate, if it says that you need cavity wall insulation, or that you need to improve your loft insulation, I've got a picture, no I haven't, then you've got to do it. Now, cavity wall insulation isn't always a good thing. So if you think your property's not, or you don't want to have it, and you're in an area of high rainfall, you can get an exemption. So it is possible to avoid that, but the exemption has to be approved by a RICS qualified building surveyor. So those are the two keys. You need your MCS certificate, you need your EPC. If your EPC says you've got cavity wall insulation or you're exempt, and your loft insulation is tickety-boo, then the way it works is that the installer actually applies for it, and then the installer advises you on whether an installation is eligible, and then you agree the quote. The installer applies for the grant, and then they send off the information at the end when it's all done, and you confirm that the installer is acting on your behalf. And it's only when the installation's done then that the grant is made available.
Marion's got a hand up again, Darleen.
Yeah, just to ask. So this scheme isn't it's accessible to anyone as long as those qualifying things that you mentioned are done. Yeah. It's not income related or anything, is it?
Nope, no. It's available to any householder. Yes.
Is that in England too, or is that just
Wales? Yes.
Yeah.
Yes.
Okay.
Yes. Yes. So it's not an awful lot. It's replaced the renewable heat incentive, which actually was quite a generous scheme, especially for ground source heat pumps. People managed to make the money back they were spending on the ground source. Air source was about 11,000-ish, but now they've cut it right back to $5,000. Those payments were made over 7 years. These ones, you get the payment pretty much up front. Some installers are saying, I mean, I'm going to put my hand up and say we're guilty, but we're saying we'll give you a rebate because it's an awful lot to expect installers to be carrying £5,000 for every customer, and then wait for the government to finally get their head around paying you back. So some installers will do that, some won't. I mean, you know, you just have to ask around. Here were the that was that. At the moment, you are aware that renewables are 0 rated VAT. There's no VAT payable. It was 5% before, but now it's 0. And if you're fitting PV and you want batteries, if the batteries are installed at the same time as the PV, they're 0 rated VAT. But if you install your batteries later, in a year's time, you have to pay 20% VAT. Yeah, I know. Stupid, isn't it? Yeah, that's why we've got such a lot of run on batteries. Can't get the stuff. Right, that was about the boiler upgrade scheme. Oh, and this was just to say, you see this on this EPC, it's saying step 1, increase loft insulation. So if you get that on your EPC, you know you have to do that before you get your boiler upgrade money. My advice would be make sure your loft's insulated before the domestic energy assessor comes out, because you don't want them charging you twice. Cavity wall insulation, if it says that, you've got to do it or get an exemption. All right. Cost of installations, there we go. Air source heat pump 10 to 18, less the boiler upgrade scheme. So if it's cost you 10,000, it'll only cost you 5. If it costs you 18, it'll cost you 13. You see what I mean?
Yeah.
And so the same for the others, 20 to 30 for the ground source, biomass about 15. Ecos for, I mentioned that one, you've had that one. Running costs. I just threw that one in. I think my head's too tired to go through it. It's kind of the running costs. It was kind of looking at new builds and an old stone cottage and a dormer bungalow. We've got a system where we can see exactly how much energy has been used on the heating system since we've installed it. With this new build, it's been running for 40 months. I'm looking at electricity at 23p a kilowatt, somewhere between, because we've got to average it out between 16 and 30p. You know, it's really hard to do at the minute. So for central heating per month, it was costing them £41. But if you look at Stone Cottage, theirs was 69, and this dormer bungalow, theirs was 87. But that's a bigger, you know, it's a bigger property. But if you compare these two, which are similar, the new build in size, you can see the new build is an awful lot cheaper. It's like half the cost to the dormer bungalow. Domestic hot water is kind of a loose cannon because it depends on how many baths and showers people take. So I don't think we can really look at that. But so there's your sort of like overall annual running costs. The new build with the hot water and the heating, 716. But if you're taking it at 40p a kilowatt, it would be, you know, the cost in a year would be about 1,200. At 40p a kilowatt on your dormer bungalow 70s build is 2.5 grand. That's just to give you a little bit of idea costs. Solar PV, we've done that, haven't we? Yeah. That was the idea that, you know, when you've got this surplus electricity, this is the red stuff's the surplus, you want to use that up. So that can go into your hot water cylinder, or it could go to your battery. In this particular case, this was a 4 kilowatt system, about 3,500 kilowatts a year. That's about right. And they usually say that if you have got without a battery, you consume about 35% of the annual generation, but with the battery, it's around about 83, 85%.
Oh, wow.
So, you know, it really does improve your consumption. They hadn't been a good idea in terms of costing, but now with, you know, that's 25p a kilowatt, we've got to be looking at that at probably 40p a kilowatt before long, the way that things are going. So obviously the more that electricity goes up, the more the savings you're going to make. That's again showing you that when the sun's highest in the sky, that's all this lovely PV that you're producing is gone back to the grid. So find ways to use it. Yeah, I think this is probably a bit deep now. It's just how it's all worked out, how much energy you get back from batteries, and you know, this is the 71% return if you had your battery, your 31% if you were just using it without a battery. So that's kind of that. And these are the sort of calculations we work out. You know, you have to work out what shading implications it has for your PV. And this is where we were talking about those little optimizers that you can get on individual panels. So if you had shading, you could minimize that impact on the rest of the array. That's just, again, you're probably too tired for that. I think I am. And that's it, really. There's a whole nother section on MVHR, but I think we have that for another time.
That's great, Darleen.
Any questions? Because I've kind of ripped through that PV stuff because you've done a lot in the early stage, so I didn't want to hammer it.
It'd be really good to see.
It's 9:30. It's 9:30.
Yeah, really good to see the slides. If you can send them as well after, and you know, it's been really good. I'm just, is it right if you stop sharing now? We'll just check if anyone's got any more questions.
Yeah, I'm just looking through here to see if these are the ones you've seen, aren't they?
Yeah.
Just give you a rough idea. Yeah. Okay. And stop sharing. There we go.
No, so
phew.
well
I think that's been a right rattle.
thank you
Well
very
done,
much.
Darleen.
It's,
very
I
clear.
mean, it is invaluable, really. Speaking for myself, but has anybody got any questions or anything they want to say?
Would anybody like us to share Darlene's presentation in full? We're starting to video some of the presentations that we're doing and sharing them on YouTube and also on our Facebook page. If Darlene's happy with it, of course, we can do that with Darlene's presentation separately. And in fact, because I think this has gone on quite a long time tonight, I might split 2 recordings of tonight, the first half and the second half. So
Yeah.
we could look at both or either.
Yeah.
Yeah, I think separate the heating out because there's an awful lot there. You know, I have ripped through it quite quickly, and you know, if somebody's new to it all, it could be quite overwhelming. And you know, I'm sure there's lots of questions from people who are maybe not involved in the industry. You know, you've got regular householders who are coming to this for the first time, and they're probably thinking, "Oh my God, you know, how am I ever going to get my head around this?" You know, there's a lot to it. But the main thing is ask questions, be aware of where the pitfalls are. You know, ask your installers, don't be fobbed off. These people should know the answers to these questions. And if they don't, then, you know, look for somebody else.
Yeah, good advice.
So just one final question on the heat pumps thing. Do you think they're worthwhile? I mean, obviously the government's pushing them massively.
Personally, yes, and in particular, if you're off mains gas. If you're on mains gas, it's probably going to be the way to go. And certainly if you're talking about climate change and you want to get rid of fossil fuels, then absolutely 100%. But it does come down to money. And, you know, we're talking some big high figures there. And, you know, I'm aware that not every household is able to do it. And that's why you need to check out these other schemes like the boiler upgrade scheme. It's not a lot of money, but it's a little bit, and every little bit counts. And Eco4, check that one out, because a neighbour of mine had that done, and he really did. He got all the radiators, all the pipe work, a new hot water cylinder, and a pretty decent air source heat pump as well. Just have to be hoping that they are all properly commissioned. But you know, some of these manufacturers they've got 7-year warranties. So if it's given for free, take it. You're eligible, go for it. You've nothing to lose.
Yeah, I think the like the countries like Scotland and Wales, possibly Northern Ireland, are a lot more generous with their funding for this than us people in England.
Does your eco not cover it then?
No, we looked at Eco4 last week, and we looked at the only people that could really go for it are the people that are actually, like I said earlier, getting either job seekers allowance or universal credit,
Yeah.
rather than sort of people like you say who've got an annual income of less than 30 grand.
Yeah. Okay.
So
I think we need to look at it in a bit more depth as well. But you know, anyway, are there any other questions for Darleen? Did you have a question, Heather?
Quick question. It's
Gail?
getting on. When you upgrade the radiators, you have to have a fatter bore of pipework that goes to it.
Oh, a fatter bore. Yeah, no, that's a good question. Now you get micro bore, which is sort of like 10, 12 mil. It's the wee skinny pipes. And then you get 15 mil pipe, which is your standard pipe. And then you get a 22 mil pipe, which is, if you imagine that as a distribution pipe that feeds the whole system. So maybe that's the artery. And then you've got the little veins are the 15 mils. If you've got microbore pipe, it does create a little bit more of a problem because it's to do with the flow rates. There are ways around it, and if you've got a good plumber who knows their stuff, they'll be able to sort it out for you. But generally speaking, microbore is a little bit more complicated. So yeah. But
so which bore would be ideal then?
Well, the 15 mil is your standard. You know, most plumbers will probably have put in a heating system with a 22 mil sort of circulation, and then they branch off on 15 mils to the various radiators.
It's just that I've seen up at Glen Eagles, it is the very thin pipe work. So I'm assuming that's the 10 mil.
Yeah, 10, 12 mil, that's the micro bore. That was very popular at one time because plumbers could just put it in and bend it with their hands. They didn't have to, you know, they could wriggle it around all sorts of wee spaces and things. But yeah, it's it can work, but you need somebody who knows what they're doing.
Okay. And any other questions then? Right, so
I've stunned you all, haven't I? It's a gin and tonics now, I think.
I think
oh, well done.
Have already started. I just want to say thank you very much on behalf of all of us, because I found it incredibly engrossing. It's the sort of information I've been wanting for a very long time, and you know, I really think that if you were in and around the Northamptonshire area, you'd be a very busy woman, really, without a shadow of a doubt.
Well, thank you for the opportunity, and I do get a bit carried away on it, you know. It's yeah, but hopefully I've explained it in a way that helps people to understand. And for the people who already knew about it, I hope I didn't teach you to suck eggs. So I hope everybody got something out of it.
No, it was excellent and very well explained, actually. Anybody else need to say anything else before we finish? And I'm noting people clapping, yeah. And there's also, I think,
just a quick question to Jonathan.
Hello, Gail.
A question from last week. I told you I'd made inquiries with something that I can't remember.
Oh, Ness. Yeah.
Yeah. What's the result on that?
I've still not heard back from them. We were talking about doing something similar ourselves, but we haven't actually talked about it yet. So it's something that I'll discuss with Heather and Marion as we move forward, and we'll see what sort of funding we can look for. But we're in the same boat probably as Ness for offering that sort of service.
Okay, thank you.
Can I just one last little thing? Somebody, the question you had earlier was it worth it, or would you do it? The heat pumps, and without a shadow of a doubt, they do work. You know, they're not just a new technology. They've been around in Scandinavia and Canada and other countries in Central Europe for years. They really do work, and they work very well in the UK. And even to radiators, 45 degrees, if your house is, you know, we fitted it in stone houses, we fitted it in houses without cavity wall insulation. They can work, and if it's well designed, it will work. That's all I wanted to say. Right.
Okay, so
Right. And on that positive note,
yeah, so thank you very much, everybody. And we're going to have a 2-week break now. So we're not here next week, but we're here the week after. I think we'll be looking at carbon footprinting and various other things about understanding our impact on the climate and the planet. But yeah, so I just want to say thank you very much to Darleen again for her contributions today, to Simon that didn't get to share his contributions, but we will share them as part of the materials afterwards. All of this recording, Jonathan, as he said, is going to break it into 2, and it's all going to go on the website. So I will be looking back at this because there was a lot that you said, Dee, that I just want to go back into again. So that's brilliant. But thank you, everybody, and have a lovely evening. And thank you to Darleen.
thank you,
Darleen.
folks. Right. How do I get out of here? Leave.
Thanks all.